Hello everyone, welcome back to this week's ASAP seminar, episode 37. We're really excited to have Jingwei Zuo from the Technology Innovation Institute with us today. Jingwei leads the Falcon team there, working on a whole family of large language models you probably heard of, like Falcon-H1, Falcon-H, Falcon Mamba, and more. Today, he's be telling us about the Falcon-H1, a new hybrid transformer Mamba 2 model that pushes the boundary of efficiency and non-context reasoning. It's open source, fast, and already competing with some of the biggest model out there. So without further ado, let's give a warm welcome to Jingwei. Yeah, Jingwei, over to you.
Yeah, thank you. Thank you, Sonin, for this invitation, and also thank you guys for organizing this seminar. I'm very happy to be here to present our work. So today I will present Falcon-H1. Is a model series based on a new design of hybrid height attention Mamba 2 model. So in this talk, I may not cover all the tiny details reporting in the tiny report. I will present more the aspects that related to the topics of this seminar. So maybe a brief introduction. This is Jingwei, currently a lead researcher from the Falcon-LM team. Our team is working on the whole life cycle of building LMs, from the data collection, curation, model design, infrastructure, the training, and the deployment. So about Falcon LMs, maybe some of you know, from the 2023, we released the first Falcon models, like Falcon 7B, 40B, and 180B. And last year, we released Falcon 2 and the Falcon Mamba 7B, Falcon 3 families. And this year, we released another three model series, Falcon H1, Falcon H, and Falcon Arabic. For Falcon H1 is a model series covering different model size, and from 0.5B to 34B. So in this talk, I will mainly focus on H1 model. And so here is the outline for this talk. So first, I will briefly introduce the context of this work, and followed by the architectural design and the decisions behind this model design. And then I will introduce some training details for this model series, including data, infrastructure, and the training dynamics. And then I will show some evaluation results. Maybe not all of them, because you can find all the results in the tiny report. I will just give some highlights and intuitions behind some results and the comparison with other model families. And then we can have some general discussions for some interesting topic. And I would be glad to engage more discussions for this part with you. So for the context, last August, we released Falcon Mamba 7B. It was based on Mamba 1 design. We didn't touch a lot the model design, except the RMS norm layer. We add another RMS norm layer just to stabilize the training behavior. And the model was trained on 5.5 tera token, and it was one of the strongest based SSM model that can rival leading transformer models at that time, like Llama 3, Mistral, and Gemma. The context length was only 8K at that stage. And then December, we released Falcon 3 Mamba. So basically, it's a CPT on top of Falcon Mamba with another 1.5 curated data source. It could be competitive with hybrid models at that time, like Jamba 2 and Jamba 1.5. The context length has been extended to 32K with enhanced STEM capabilities. Actually, for Falcon H1, we started this project just after we released the Falcon Mamba 7B model around August of 2024. And during the past 8 months, during the past 1 year, we have observed a big progress in the community. for the hybrid architecture design, like to combine attention with different linear attentions, and how to tweak this hybrid design by changing the layers and the attention ratios, and also by optimizing the linear attention blocks. Those are very interesting work, and we keep following them. And here is a glance on the literature. And maybe most of you are very familiar with most of the models here, the hybrid models, from the initial Jamba model, Zamba, Samba, Himba, Minimax of last year, to the recent Hunyuan, Nemochong, Granite, 5.4, and Jet Nemochong models. It's very interesting to see all these models emerged with a hybrid design, and proved that this hybrid design can bridge the attention and SSM and fulfill some constraint of the linear attention blocks, especially for the non-context processing part. It's very interesting to see many of the models, they focus on different aspects, like for the efficiency or the memory optimizations. So maybe here is a global view for the three different popular designs, for three popular hybrid designs: the fully parallel, semi-parallel, and fully sequential. Most of the current hybrid models, they fall in the scope of fully sequential. Like we can have the interleaved attention and the non-attention layers, and followed by MRP layers, and all the forward paths will be sequentially passed by except Himba is an interesting work, very similar to Falcon-H1. I may have some discussions later. As the first step, when we designed the H1 models, we did exhaustive studies and tests to compare these three different variations, three different hybrid designs. So as a starting point, we check the attention fraction. And for instance, we pick we pick the fully parallel design, and can find out the optimal attention fraction would be 1/8. And then with this optimal attention fraction, we can have a fair comparison between these three hybrid designs. And we found out that the semi-parallel shows the best training loss. And we did some other tests, like to select the best attention fraction from a semi-parallel or fully sequential design, and all the conclusion will maintain the same. A lot of studies shows that they can find optimal attention ratio in the hybrid models. But I would say with different hybrid design, maybe we need to redo this process, because the interactions between attention and the non-attention might be different across different hybrid designs. And then we have revisited almost every aspect from the SSM module, the Mamba2 module, from the Mamba state size, number of Mamba groups, height dimensions, convolution kernel size, and chunk size. And some of the tests were not seen in other papers, and it will be very interesting to do all these tests by ourselves and get more insight and also other conclusions. So first, for the state size and the number groups, and clearly with the larger state size, the model performance will be much better, but with the sacrifice of the throughput. And then for height dimension and the convolution dimension, just no big surprise. Like we can always find the sweet point with a bigger height dimension, the performance will be better. And for the convolution dimension, the conclusion stays the same as the official paper. We just picked 4. And another aspect we're interesting to mention is when training on the non-context data, especially considering the packing design. Usually for attention, we have some mechanism like cross-document masking that can simply mask out the attention scores across document boundaries. Is to avoid some semantic contaminations issues between unrelated context. And for recurrent models, we may have similar designs or techniques to handle this issue. And a simple trick is just to initialize or reset this hidden state as the boundary space. For instance, let r equals 1 signify the location of the first token of a new document in the sequence. We can at this boundary we can just reset the hidden state of the at this time step. So we will just keep a very small stepwise value for xt, and we can do this by simply injecting a very large negative value -80 at channel wise. Why we choose this value? Because it's still falls in the scope of the BF16 or FP16 underflow threshold. So we will not have the zero gradient, and that can avoid the training instabilities. During the training of Falcon-H1, we observe some practice that may not be aligned with the conventional tricks in the domain. The first one would be the Ropicita. We did the tuning during the pre-training process, and we found out the optimal value is around 1 in minus 11. Sorry, and then 1 in minus 11. That is much larger than the commonly used value in the transformer models or hybrid models. And so here is an open question, like this large European theta value, will it work only for the sequential hybrid design, no, only work on the parallel design, or it can also work on sequential hybrid or transformer models? One assumption from outside is for the SSM part, it can handle perfectly the short context data. And then for attention part, even though we set a very large Ropicita, it can focus on the long context data. So both of the head can do their job very perfectly. And another interesting observation is the width depth trade-off. And recently, we also see other models have this practice, like GLM 4.5. They have applied a deeper design compared to DeepSeek V3 and the Kimi K2. And in our test, we did several sweeps over the width and depth of the models, and we scaled the learning rate inversely with the width following the MUP scaling. And with several architectures of different depths and widths, we found out a deeper model can indeed show much better training loss. And also from our end-to-end training and evaluation result, the deeper model shows much better performance. And but this just no free lunch. Like with a deeper model, with a deeper design, we need to sacrifice the training and the inference throughput. That's for sure. So all depends on the application scenarios and the use case for these models. So finally, we have released two model variants for our 1.5B model, one with 24 layers, the common design, and the one with 66 layers, the deeper one. We could release even a deeper model, like 87 layers, but in that case, the throughput will be crazy. But from our internal test, this very deep model can match or even outperform our H1, 3B, or 7B checkpoint. And I think in the technical report, we also showed this comparison with other leading transformer models. our 1.5B deep can rival or even outperform the current leading 7B model, like 0.2.57B. So here is the final architecture design of Falcon-H1. Like we can see the parallel head of SSM and attention. Just need to mention here, the architecture design is quite similar to Himba. And it's very interesting to see different work and different team converge to similar direction. And one big difference compared to Himba design is here, we can have the flexible ratio between SSM and the attention within each block. And then for the Falcon-H1, different decoder layers, we applied exactly the same blocks for consistency. And for Himba, the way to modify the ratio of attention would be changing the number of attention layers or switch the full attention to sliding window attention. And in this model family, we have 6 variants. Each of them was trained with different tokenizers and tokenizers with different vocabulary size. Also with different training token budget from 2.5 tera token until 18 tera token. That is much less than the current models like Queen 3 based on 36 tera token. One important part that we want to mention is the training stability of the models. Especially when we scale up the model size to 30B or 34B scale. In small model scale, from the very beginning, we observed the model was quite stable. And if we just add the arms norm, it can handle most of these spikes. But it's not the same case for large models. So one of our proposal is using MUP transfer to stabilize the training process. And another advantages of MUP is that it can allow us to use very high learning rate, and it can give us other possibilities to do CBTs because the model can adapt very quickly when there's a distribution shift of the data. So basically, we have manually tuned the 35 multi-multipliers, and with some iterative process of 10 stages, more than 500 rounds. Okay, then for the pre-training infrastructure, we have applied our in-house training framework with 5D parallelism based on Falcon-H100. We have redesigned the context parallelism for hybrid attention Mamba 2. We also have proposed the mixed parallelism for the parallel head of attention and SSMs. And I may give more details later. Okay, and for different model size, the context support will be different. At 0.5B, we have up to 16K because the small models cannot handle this long context data. Will be a bit too complex for them. And then for 34B and 7B, we have to 62K, and others we have 131K. Okay, one of the innovation in H1 design for the training and inference is on the mixture parallelism. So during the training, even before the training, when we did the test, we observed the imbalanced distribution of the computational and memory overhead between different head, between SSM and the attention head. If we just use the tensor parallelism, like the overhead between GPUs and different ranks will not be balanced. So here is a very simple trick. We can repartition the TP ranks regarding the SSM and the attention head. Means it's kind of rebalance the computation and the memory between GPUs. And from the result, for the training efficiency, we can have the boost around 40%. And for the inference, it can consistently give better inference efficiency compared to the default design. Okay, then we come to the data and data strategy. That should be the most important part nowadays for LLM training. From the very beginning, we have redesigned and rebuilt our tokenizer, Falcon-H1. And we believe that for different model size, we should apply different tokenizers of different vocabulary size. And this tokenizer has been trained with, on top of more than 100 languages. So for the CPT continued pre-training of Falcon-H1, it can be easily adapted to the new languages. And during this, when we build the tokenizer, we realize that some classic metrics like fertility score or the average numbers of bytes per vocab token, are not the only criterion to evaluate the tokenizer's quality. And most of the time, we need to launch the end-to-end training to decide some intuition-based tricks, like whether we need to apply punctuations or digit splitting, or the importance of LaTeX token on math or coding skills. And then for the training data, as mentioned, we have the training budget between 2.5 teratoken and 18 teratoken regarding the model size. And we did extensive explorations and processing for the raw data. And we validated all the data source before we ingest them into the training. And also during this iterative process, we can the skills. So for the data mixture of the big models, 34B and 7B, we modify the data mixture on the fly during the pre-training process. And we monitor closely the performance on different domain tasks. And more importantly, we do the web checks for different checkpoints during the pre-training process. That can avoid some unintended bias on some domain-specific task, and to ensure the generalization of this model series across different tasks. And then for the data strategy, that's something which are also different compared to some common practice in the domain. We applied the multiple epoch training regarding different data source, and one important part is to check the model memorization and forgetting window. This part is extremely important if we consider the very limited high-quality data. From recent papers and research, for high-quality data, we can repeat multiple times. Like from 5.4, we can repeat up to 40 epochs. But the key problem is that how we can organize this data into different training stages, how we can distribute them across different memorization window, and because if we upsample this data equally across these pre-training stages, maybe two identical samples will be seen at the same time or consecutively. That will impact a lot the model performance. Also, we applied anti-curricular learning in pre-training. Instead of having multiple stages and increasing the data quality gradually, stage by stage, we apply the best quality data from the very beginning. And then for the pre-training, the contest, different from other models, most of the pre-training stage was on 16K contest. And we have the final extension stage to extend this contest up to 256K. Okay, and then for the evaluation, as I mentioned, we did frequent evaluation during the pre-training, and we check very frequently the evaluation results on different benchmarks across different domains to capture better signals. We also do very frequent web checks on intermediate checkpoint using a set of custom prompts, different domain tasks. Okay, for the evaluation result, I may not show all the results across all the model size and compare with different model series. That will be too heavy. So here I will just show the aggregation of the benchmark results across different domain tasks. We compare basically with other model series like Queen 3, Queen 2.5, Llama 3, Gemma 3, and Falcon-H1 across different model size. And here in this slide, I show the general task, instruction following task, multilingual, and the science. We see that Falcon-H1 model series consistently outperforms other model series. And something interesting to observe here, if we compare Queen 3 and Queen 2.5, we see that Queen 2.5 performs even better than the recent Queen 3 models. That should be mainly due to the updated data mixture from Queen team. Another two domains from math and coding. Falcon-H1 is lag behind Queen 3, and for math we lag behind Queen 3 and Gemma 3. For coding, we are comparable to Queen 2.5 at a large scale, but much better for small scale models, but still lag behind Queen 3. So from all this high-level comparison, we can see that recent model series have shifted their strength and focus towards math and reasoning intensive tasks. But for some general and knowledge intensive tasks and domains, the performance even degrade. Another thing would like to mention is the model comparison beyond architecture. So usually to compare all these model series, it's very hard to have the apple-to-apple comparison. And most of the performance will be decided by the data mixture, that's clear. And this data mixture I think is mostly decided by the business use cases and model positioning and real-world deployment scenarios. Different team and the models, they have their own preference and focus. Maybe most interesting part for the hybrid architecture is on the long context performance. We show that Falcon-H1 34B performs very good on the RAG task, much better than other models like Queen 2.72B and Queen 3 Llama 3. But with comparable result on recall and non-QA with Queen 2.5, but lag behind Queen 3 and Llama 3.3. From our studies and experiments, it seems that most of the cause are from the data mixture. For the hybrid design, seems not from the model design perspective. But I would be happy to have more discussion with you guys if you have more insight on this part. And then finally, for the model efficiency, we compare H1 34B with Queen 2.5 32B, and we test the prefiling and the decoding throughput. And we observe that for prefiling, we can have up to 4 times speed up, and for the decoding throughput, we can have up to 8 times speed up. Okay, and another interesting result to show is the model depth. As mentioned previously, for Falcon-H1 small models, we performs much better than the leading models in the literature. For 1.5B is the SOTA 1B scale model to date. And if we compare 1.5B deep and the 1.5B, almost on all the benchmarks of all the tasks, the deep model outperforms, and with a big gap compared to other models at 1B scale. And for most of the benchmarks, the deep version can match or surpass Qwen 2.5 setting. You can check more details in the technical report. Okay. And then for the integration and the support in the open source frameworks and in this ecosystem, Falcon-H1 now is supported in most of the popular frameworks for different usage, like the general usage, fine-tuning, local cloud deployment, quantization. And we are closely collaborating with different community partners to integrate more frameworks in this picture. Okay, so some general discussions on different topics. For the model architecture, as I mentioned, it should set the lower bound of the model performance, and most of the time it will define the key characteristics of the model, like the efficiency, memory cost, etc. But for the upper bound of the model performance, it's always decided by the data mixture, and it may have much stronger impact than the architecture itself once the lower bound is guaranteed. And there are a lot of anti-intuition observations during our training process. For instance, a lot of common practice or research conclusions, they may only valid under some specific conditions. And there will be some surprise when we scale up the model size using a new architecture. And when combining with other variables, other factors like non-context, or to validate this performance on larger scope of benchmarks and domain tasks, it will be very hard to have a balanced performance across all the tasks. And the model performance is always decided by the interdependent factors. So as I mentioned, it's very hard to do the ablation studies just to decide the impact of one specific tricks or one specific factors. We need to have multi-dimensional optimizations guided by the experience and the exhaustive test. And for some of our future work of Falcon-H1, we may think about extending the context length beyond 256K, at the same time to improve the non-context capability of the existing context length. We will keep working with the community partners to optimize the inference with different frameworks like VLM, Llama CPP, SGLang. We will, in this presentation, I didn't mention too much for our post-training and the reasoning capabilities of the model. Is some work we are going to further push and currently working on that. But from some preliminary results, we didn't see any constraint from the model architectures. Most of the learning behaviors and the learning curves, they are very close to the pure transformer designs. And also we aim to improve the token efficiency in pre-training, like with limited training tokens, how to maximize the knowledges learned from these tokens, and to shorten the training durations for large models. We also need to, we will also enhance our data mixture and data corpus with broader, more diverse and high quality data sets. Yeah, thank you. That's all. And here are some takeaways, some links for our technical report, GitHub, blog post, and Hugging Face collections. And yeah, that's all. If you have any questions, I'll be happy to discuss.
Yeah, we have a question in the chat. I'll read the question. Your slides on the memorization window during pre-training was very interesting. Could you talk more about it and your observations there? If there's related published work we can look at, that would be also helpful.
Yeah, actually, here should be the most interesting part in our data strategy. From what we know, to the best of our knowledge, they are not. I mean, there's some work in the literature to discuss the multiple epoch training and the memorization and forgetting behavior of LM. But most of them, there are some individual piece of the work. Is not some very complete work at the system level for LM training. So some work may analyze uh, the impact of the multiple epoch training, but in this work, maybe they didn't consider the memorization window, and they didn't consider the how to distribute the training tokens of the same data source within the window or beyond the window. Okay, so if we go back to the memorization window in this work, so basically, we used our some internal checkpoint models of different size to check. The first step is always to check the training loss. If we repeat the data every 20 GR token, 100 GR token, 500 GR token, will the training loss have some difference, or will we see a big drop of the training loss? That's something we see here in the plot. If we repeat every 20 GR token, and then we see an immediate drop at the beginning, means the model memorize all the information in this data. And after this 20 GR token window, we go back to the unseen data, and then the training loss comes to the normal one. So by this kind of experiment, we can estimate roughly the memorization window of different models or different model size. And I hope I answered your question, and I hope I didn't go too far.
Okay. So if you have any questions, please feel free to unmute yourself or just drop the question in the chat.
Yeah, I think it's the following questions in the chat again. Yeah.
Yeah, I'll read the question. Do you see a general window like a phenomenon when it comes to learning and forgetting during pre-training? And any related work that may be published by others?
Okay, so for the first question, I can see that we have for this window we have did some tests, like for instance, for 1B model, we repeat every 50 GR token, and we validate the final performance on different benchmarks like math, STEM, and coding. And we can see that during these 10 epoch or 10 windows, the performance keep increasing. There's no saturation. So we can see that the model didn't overfit on this window data, on the data falling in this window. And if we shorten this window size, we can see a different performance curve or performance behavior across different training epochs. The model will saturate very quickly. Yeah, but some related work we haven't seen yet, and actually from outside we are considering to have some continuous work on this and publish.
We have another question in the chat. Could you share more about anti-curricular learning in pre-training? Is there any gain from these data strategies?
Yeah, actually, the anti-curricular learning is more or less related to the memorization window and the multiple epoch training. Imagine that we have very limited high-quality data source. The curriculum learning will be injecting this high-quality data source at the end and just use some general corpus like web corpus from the beginning and increasing gradually the high-quality percentage. But in that case, the training epochs for no, the training epochs for this high quality data source will be limited if you just inject at the end. But if we inject from the very beginning and by combining with this memorization window, we can repeat this high quality data source by multiple times, like 10 times or 14 times. And from the in theory, we can say that the complicated the complex data or the high quality data from the very beginning can set up a very can initialize the model to have a better starting point for the model initialization. And this model can learn from the very beginning the knowledge and the behaviors from this high quality data and the complex data.
Yeah, maybe I have one question. I see that on the infrastructure side, you said that you use the mixed parallelism strategy that which means that separate the attention and the SSM blocks. Yeah, but I'm thinking about especially in the during inference that when we have different contact lenses, the cost of these two components, their balance will shift. How we can ensure that we can have a balance allocation on the hardware resource into both the two types of the head. Yeah.
Yeah, that's a very good question. And actually, for the inference part, for VLM, for instance, for VLM of different context lengths, that depends how you design the MP values during inference. That could be a very flexible value. If the attention part take more memory, we can adjust very flexibly the proportion of GPU to be put in the attention part. Then we can decide we can change slightly the MP values. But I agree for different context lengths, we need to change flexibly the MP value.
I see.
But yeah, but here is not a fixed value; it's a flexible value we can set.
I see. Yeah, this makes sense. Yeah. I guess that if you want to make it more efficient, maybe some dynamic one, yeah, even
Yeah,
needed.
yeah. Okay. Okay. Any other questions?
Let me ask you a question. So did you have like any ablation study on the hybridization strategy? For many work, they just interleave their SSM modules and the global attention module, but you use the hybrid head strategy like Himber. So did you observe like a significant improvement over those interleaved models?
You mean some other experiment beyond this the experiment shown here?
Yeah, do you have like some like preliminary ablation study, although you didn't show it in the paper? Like, could you like share it? Yeah, because like this hybridization strategy is very of interest.
Yeah, actually here, I think in the paper we show some high-level ablations, like for these three categories: the fully parallel, semi-parallel, and fully sequential. And for Himba design, it falls into the semi-parallel design. And basically for the Himba block, we equally split the attention and the SSM head. They have 50% and 50%. And then for Himba, they will most of the ablations in Himba, I mean, if we want to apply Himba design, most of the ablations will be pick the optimal full attention layer or SWE layers and then do these ablations. And but that will be some work orthogonal to this work. Like we can always pick that one and do further ablations, but there's no conflict with, I mean, with the semi-parallel design that we shown here, because even though now for Falcon-H1 we use the same design across all the layers, but we can also put some layers with SWE or pure attention, pure SSM. But there should be some other work beyond the scope of this project.
Yeah, thank you for explaining. I think there are multiple hybridization strategies. Like the most simplest one is interleaving between SSMs and the attention modules. And there are some work trying to have both the SSM and attention within a single layer. And you use the hybrid height. Basically, you split the height into two categories, and they are still separated to some extent. And I think there's another type of hybridization strategy. Like for each head, you have both the attention part and the SSM part. Like for example, you can use like a sliding window for nearby token and use another R modules to summarize the entire history outside of the sliding window. Yeah. Have you ever tried hybridization strategy?
For this, we didn't try.
I see. What's your expectation of this hybridization strategy? Do you think it will like improve the performance further?
Yeah. For me, for us, we believe that it will further improve the model performance. I mean, not only we believe that the hybrid design should be a very promising direction to follow, but there are some challenges we must face that will be more for the practical usage and how to, because there are a lot of optimizations for the transform part and attention part for the integration framework inference, and there are very limited work on the linear attention part. And to have the better adoption by the community and by people, and I mean, more effort should be done from this aspect.
Yeah, totally agree. I think the VRM and the SGNN community are actively supporting hybrid architectures nowadays because there are a lot of hybrid models. Yeah.
Yeah.
And also I think in this technical report, I think like the ablation study on the depths of the model is quite interesting. Do you have any plans to train deep models for larger scale?
That always go to the engineering effort. If we can ensure the deeper model at large scale, they show similar inference throughput, then why not? And I think the model performance and the design is very promising, but how we can land this model for usage is another factor to consider.
I see. Yeah, so you are concerned about like the inference efficiency for larger models. So
yeah.
Okay. Another question: have you ever tried MOE model training, or did you experiment with dense model for most cases?
We do have some experiment and internal studies on MOE models, and yeah, a natural practice will be combined these MOE models and these hybrid designs. And I don't know if in the literature there are already some practice or not. Yes, there is. But most of the models are still on small scale, like like Granite 4.0 tiny preview, and they're still on 7B scale MOE model. But it should be a very promising direction to go. But still, like the most of the concerns from the adoption and compatibility with the ecosystem.
Yeah, I agree. I totally agree. Yeah, I think yeah. So do you think the hybrid model will take over like become the like mainstream architecture if the ecosystem become more and more better?
Yeah, definitely, I agree. I believe.
Yeah. Do you think like the attention the RM module matters? Like have you ever tried like more advanced RM module like DataNet stuff like that?
Pardon?
Have you ever tried different RM modules rather than member like gated DataNet?
I think that would be something for next step or something we are going to do now.
Do you have some like preliminary study?
Yeah, I saw the recent model, the Jet Nemotone, and also the Getty DataNet.
Yeah.
Yeah, I think should be a very promising direction to go to check. But I'm still curious, like maybe a question from my side. Uh, I saw there a lot of work, I mean, maybe from your part and from the community to optimize the performance of linear attention, just to align some of the skills with the attention models. But in the context of the hybrid models, for me, all the skills of attention and non-attention, they should be complementary to each other. So if we improve the non-context processing of linear attention layers, will it be redundant to the attention part in the hybrid design?
Yeah, I think I totally agree. I think like the linear attention like functionality should be made in the hybrid attention setting, so to better compare them. I think ByteDance Seed they presently have a recent work like just pre-training a bunch of hybrid model from scratch to see the impact of the linear attention components, right?
Yeah,
And they
yeah,
have
makes
some interesting and counterintuitive results. Yeah, I think this is also very interesting.
yeah.
Okay.
Yeah, I see in your design that maybe the current ratio of the SM head and the attention head is nearly half to half. Yeah. Yeah.
Yes, for some of the, let's check this one. If we check the number of head of QKV, SSM, and D head, yeah, for
Yeah.
some of the model size, they're quite close.
I see. Yeah. For the larger one, it seems that more close. Yeah. Do
Yeah,
you have some more aggressive ones that with much fewer that attention has? Yeah, because I see that in some recent designs that people tend to be very aggressive.
yeah. Actually, the optimal ratio we found in our preliminary studies, we didn't apply them to all the model size, just mainly considering the engineering perspective. If we consider the tensor power region and the mixture power region, then it should be divided by 8 or by 4. Then we must have the times of 8 of SSM head or attention head. We may need to have some sacrifice when we go to the engineering labor.
I see.
But in terms of the extreme crazy ratio of SSM or attention, I mean, after the preliminary studies in our test, we didn't observe very good results, and then we didn't go that direction.
I see. I see.
But as I mentioned, for different hybrid designs, the ratio should be different. That's for sure.
Yeah, yeah, yeah. I think they have different abilities. Yeah, so maybe I change some of the ratio. Yeah.
Yeah.
Any further questions? Okay, let's wrap up out here. Thank you again for your talk. Yeah.
Okay, thank you very much for organizing this seminar.
Yeah.
Very nice to meet you.
Yeah, let's see you again.
Yeah, very
I'll
much.
start recording.